The plan for today's class is first we'll talk about a specific way of parallel processing using R. Okay, we looked at R Hadoop and R RMR and RHDFS. That's like doing Hadoop style processing using R. And today we'll look at slightly a different model of doing parallel processing using R. And after that, we will kind of wrap up all the concepts and then talk about the project. And as we discuss the project, I'll briefly touch upon linear regression and logistic regression. Okay. Okay. So essentially, we are going to look at what is called as Foreach package. Okay. The package name is called Foreach. And there are a couple of other relevant packages which we will see as well. Okay, and the goal is okay. I think there are a lot of introductory slides which we don't need to go in detail, but essentially what it says is serial computing is doing something on a single machine, and parallel computing is doing the same thing on multiple machines, and not surprisingly, doing it in parallel on multiple machines is likely to be more efficient than doing it on a single machine. And how do I enable that style of computations in R? Okay, that's the primary value proposition of this Foreach package. Okay. Yeah, we all know this. Why use parallel computing? To save time and money. That's fine. Blah, blah, blah. Yeah. So we always, we all know what is the importance of a looping construct, right? You have a set of elements and you want to loop over those elements and do something on each element. That's a very common very common access pattern in your programs. Okay, and a lot of times, more than you think, independent processing of individual elements is also quite popular. Meaning, if I have a list of 100 elements and I want to do something on each of the element, let's say add 1 or add multiply it by 2, that is totally independent of each other, right? Whatever processing I do to one element is completely independent of the processing that I do on a different element. Okay, that's an independent processing of the list of elements. And because of that independence, it's quite natural to think of that computation being done in a parallel setting as well, right? If I have 100 elements and 10 machines, then I can simply provide 10 elements to each of my machine, and they all process these 10 elements in parallel, and then they get back with 100 results, right? It's an embarrassingly parallel problem. And even though it's embarrassingly parallel, in practice, you will actually encounter many situations where that style of computation is present. Okay, and in R, in native basic R, there are many looping constructs. Okay, looping constructs meaning applying something on loop through a list of elements and apply some computation on each of the element. Okay, and those are typically called as apply functions. Actually, learning R will always be incomplete without learning about apply functions. I, in fact, wanted to discuss at least 30 minutes or 1 hour in one of the classes to touch upon these apply functions, but we never had time for it. And there are many variants of apply, L apply, S apply, R apply, blah, blah, blah. Each one essentially differs in the way they return the results and the way individual elements are treated and stuff like that. But the core concept is essentially loop through a list of elements and then do some processing on each of those elements. Okay, and this R for each package is kind of yet another looping construct that you can provide. Okay. Okay, so yeah, for each package executes in parallel, so it saves time. That's fine. Okay, so before we see what we can do with for each package, I should mention that even this for each package is designed by this company called Revolution Analytics, which is the same company that designed RHDFS, RMR, RHBase packages. Okay, so the same folks have come up with this for each package. It's essentially the beauty of this for each construct is that your ability to specify the computation just like the way you used to do in traditional programming languages, including R, but still do this in parallel. Okay, and it looks like this. So in this example, the goal is to simply compute the square root of all my elements in the list. Okay, and in this, the list of elements is just 1, 2, 3. Okay, so I'm simply specifying. So how would I do that in a regular C language or a Java language, right? I would say for I equal to 1 until 3. I open the parenthesis and I'll say square root of I. Okay, and then get that square root and put it in, let's say, result array, which is indexed by I again. Okay, that's how a simple for loop to construct square root of all the elements would look like, right? And as you can see here, the look and feel is exactly the same. And I still have the for loop. Instead of simply for, I have for each. Okay, but that's a minor difference, but it still has the similar feel to it. And the only difference is this percentage do percentage. That's a special syntax which kind of gives handle to for each package that the following set of statements need to be executed on the list of elements that we are passing it on the left side of this particular expression. Okay, so the look and feel of the entire statement looks like a regular for loop, except that it can run in parallel. Okay, that's the primary goal of this for each package. So actually, let's look at some examples and then we'll just go through the slides. Okay. So you will see this part of the code on LMS website. So don't worry. And just like any other package, we need to first install the package, and that's what that you can do through something like install.packages, right? I already installed, but I can do install again. But let's not do it for now. Okay. Let me do one thing. Oops. Just give us 1 second. Okay. And once I install, I obviously do a library to load that particular package so that all the features that are available in that particular package are now usable in my R session. Okay, and I can explore the package also by going to the list of packages I have. I click on it, and then I can see what are all I can do. Right, there's %2, %2 par %, and the for each command that we are going to look at, and so many other things. Okay, and so this is an example that we just saw on the slide. So I'm simply saying for each, I equal to 1 to 3 and do square root of I. Okay, and if you look at the result, you get obviously square root of those three elements. Square root of 1 is equal to 1, square root of 2 is 1.4, and similarly square root of 3 is 1.73. Okay. However, all the set of results are kind of concatenated into a list. Okay. So if I say result, can all of you see what I'm typing? Okay. Okay. So if I say result is equal to Foreach, and how would I check the type of my result variable in R? I want to see what is the type of that particular result. So can anybody tell me how to do that? Exactly. I would use class. Okay. If I say class of result, I get list. Essentially, I'm computing the, imagine you are doing it in parallel. I mean, it didn't do it in parallel because I'm still running on a single machine and I did not specify any parallel constructs in it. But imagine you are working in parallel and you have three machines. Okay. The first machine gets the work of computing square root of 1. The second machine gets the work of computing square root of 2. And the third machine will get the work of computing square root of 3. Okay. Each one produces results. First one produces 1, second one produces 1.4, third one produces 1.7. Right. Now, the way you combine all these individual results is simply by creating a list of these results. Okay. So the result will be a list which contains the first result, second result, and third result. Okay. And obviously the number of elements in this list is equal to the number of elements in the input. Okay. So my input is simply 1:3, which means 1, 2, 3. There are three elements, and therefore my output will contain three elements as well. And we can see that length of my result is equal to 3. And how would I index into my result? We have seen that we will say 2 open parentheses, right? That's how we index into the list, if you remember. If I simply say 1 parenthesis or 1 open bracket and 1 closed bracket, then I get the first component in the list. Okay. So actually, if you see here, you will see that the first component is the result from the first machine, which is 1. And the second component is the result from the second machine, which is 1.4. And the third component is the result of the third machine, or the third input element is 1.73. Okay. So what you get out of Foreach is a list of results. Okay. And you index them into the list just like the way you do it on a regular list. Okay. It simply applies whatever, okay, it looks like at high level, it looks like that. For each, you specify inputs and then percentage do percentage and you specify computation. Okay. So it's not the right syntax, obviously it will fail. But what it's saying is you're applying this computation, whatever you specify. It need not be just one statement like here, square root. It can be a list of elements, or it can have its own loops and stuff. Any program, any R program. Okay. It applies this particular computation on each of the element in this particular inputs. Okay. And that's essentially what Foreach does. So here we are not the inputs here. Okay. This one, it's not really like an array, or it's not, we are not incrementing something again and again. Okay, we simply treat this input as a collection of elements. Okay, so there is no increments here. The collection in this particular example is 3 elements, which are 1, 2, and 3. Okay, and instead of specifying 1, 2, 3 separately, I specified as 1:3. Okay, but I could have done for each I is equal to C of 1, 2, 3, and then percentage do percentage blah blah blah. Okay, I could have done that as well. So there is no increment here. We simply have a list of elements, and we are applying computation on each of those elements. And in this particular example, that list of elements is produced by a sequence construct, which is 1:3. Okay, does that make sense? I is like a loop variable or an iteration variable, just like the way you think of iteration variable in regular for loop or a while loop. Okay, however, it's just a iteration variable which will not get incremented one by one. It simply gets assigned with a different value in each of my for loop. Okay, again, think of this as a list of inputs or the list of input elements, and then I is just a way to refer to individual elements. Okay, it's not like you are incrementing I and then going to individual elements. So I is simply a way to refer to the input element, and that's why you can use it in the computation. So in this entire computation, whenever you refer to that iteration variable, you are essentially referring to one of the input element. Okay, you will see more examples, and probably that will help you understand. Probably this one helps you understand. Okay, here in this example, I have two. So in the first case, we just have a single list of input elements. Okay, which are 1, 2, 3. But imagine, let's say we have two inputs. One is 1, 2, 3, and the other one is 10, 20, 30. Okay, and I want to add these two lists. Okay, so I have let's say L1 is equal to C of 1, 2, 3, 4, 5, or I could have done C L1 equal to 1:5, and L2 is equal to sequence of 10, 50, 10. Okay, so L2 is 10, 20, 30, 50. L1 is 1, 2, 3, 4, 5. Okay, now I have two lists of elements, and I want to add those two lists element wise. Okay, so I want to add 1 plus 10, 2 plus 20, 3 plus 30, 4 plus 40, 5 plus 50. Okay, and that's something you can do by, again, for each package, for each construct. So I would say for each, my element 1 is, let's say I specify A is equal to L1, B is equal to L2, percentage do percentage, and A plus B. Okay, so here again, imagine my inputs to be a list of input elements, right? It's just that I have two lists of input elements. One is indicated by A, other one is indicated by B. Okay, and just like the way you divided your 1, 2, 3 into 3 different machines, now we are dividing our two input lists, which are L1 and L2, into multiple machines. Okay, correspondingly. By corresponding, I mean wherever the first element of L1 goes, the first element of L2 also goes to the same machine, right? These are two input elements, so they are kind of aligned together, and then they are partitioned across multiple machines. And then on each of those partition of input lists, we are applying this particular computation. Okay, and now you can see that A and B are simply a way to refer to individual elements in this particular list, and that's why they are called iteration variables, and therefore they refer to individual elements in the list. Okay, and if you are familiar with high performance computing, it's called SPMD. Okay, it's called single program multiple data. It's the same program that you're executing, the same computation, but on multiple data points. Okay, that's where the parallelism is getting instantiated. Okay, and so obvious things that you can try out is, what if my two input lists are not exactly of the same size? Okay, in first case, I mean in one case, my length of L1 is 5, and also length of L2 is also 5. But what if my length of L2 is something else? Okay, and that's exactly what's done here. It's just that my L1 is 1:3, so it's a list of 3 elements, and my L2 is a list of 4 elements. Okay, let's execute the first one. That's obvious. I'm just adding 10 to each of my 1, 2, 3, so I get 11, 12, and 13. Okay, if I do this one, okay, my L1 is 1, 2, 3, and L2 is 10, 10, 10, 10, 4 times. Okay, so length of L1 is 3, length of L2 is 4. And in this case, we just simply ignore whatever are the unaligned parts. So we only take the aligned parts, which are still 3 elements. Okay, so I still get 11, 12, and 13. Okay, and in this particular example, in the third one, my L1 is 1, 2, 3, and my L2 has only 2 elements, 10 and 10. And in this case, the result will contain, can anybody guess how many elements will be there in the resulting list? So we just said that we will get the result only when the element from both the lists are available. So only the aligned ones. Okay. So we actually get only 2 results because those are the aligned ones, right? So I get 11 and 12. And for the third element in list 1, which is 3, I don't have the corresponding element in list 2, and therefore I will not get any result for the third element in the list 1. Okay. Okay. So far we simply, actually, I don't know if you are familiar with MATLAB. If you are familiar with it, there is also a construct in MATLAB called parser, which has similar flavor to it. Okay, parser in MATLAB, if you are familiar with it. Otherwise, just ignore whatever that is. Okay, so far what we did is simply apply a part of computation on individual elements, and then the resulting list or the resulting set is a list of individual results produced from each of our machines. Okay, that's one, that's already powerful and it's useful. But in some cases, you want to apply some kind of a aggregation or a combined function on each of these results. Okay, it's like, I mean, it's like MapReduce, right? Whatever you did so far is simply mappers. Okay, what does mappers do? It applies the map function on every element, every key value pair in the input, right? And produces another key value pair. And similarly, that's exactly what we did. We took this computation, which is like a mapper, and applied it on individual input elements. Okay. And what is the role of reducer? The role of reducer is to take all these input elements and then kind of combine them together. Okay. And the same thing you can kind of get in Foreach package as well, using the dot combine method, dot combine parameter to Foreach function. Okay. By specifying this dot combine, I can tell how these individual results need to be combined. Okay. The default combination is simply putting them all together, slap them one on top of the other, and make it a list of elements. That's the default behavior of combine. Okay. But you can specify your own combine function as well. And in this example, let's take only the aligned case. So this is combine using C. Okay. So here, instead of creating a list of individual results, I want to put them all together and create an array of elements, array of resulting elements. Okay. And we all know what C does, right? I hope you remember. So C of 1, 2, 1, 5, 10 will simply create an array of 3 elements with 1, 5, 10. So if I say class of C of 1, 5, 10, then I get numeric, which is like a array of numeric values. Okay. So in this case, I want to do A plus B, except that I want to return it as a array of elements. Okay. And that's why I specify dot combine to be the C function. Now if I execute, I get an array of 3 elements, 11, 12 and 13. Whereas previously, remember, we get a list of list with 3 components with 11, 12 and 13. Okay. See the difference? So result 1 is equal to, let's take this one, or let's say result. Okay. Result combine is equal to with C function. Now if you see class of result and class of result combine. Okay. In one case it is a list, in the other case it is just simply an array. Okay. But you can see length of result is 3, and then length of result combine is also 3. Okay. Except that by specifying this combine function, you are specifying how these results need to be put together. Okay. And this is just putting them together and creating an array. But obviously I can apply any function as well, any other function as well. Just like you do it in the reducer, you can specify any other function as well. In this next example, I'm specifying sum as my combine function. Okay. So I just don't want to put them one after the other and creating an array. Instead, I want to sum all of those individual results. Okay. So what would be the result of this statement? Okay. We add the results of A plus B and I get 36. Okay. Which is essentially 11 plus 12 plus 13. Right. So, oops. It's essentially doing sum of result result. Oops, doesn't matter. Okay, it's essentially like sum of result combined. Okay, so it's pretty straightforward, right? I hope everyone is following. Okay, so that's the way you specify the combine method to this Foreach package. Okay, and obviously there's other things that you can do, like you can specify the init value of the result. So if I say init value is 100, then all my sum will be added to the init value. Okay, and obviously by default the init value is 0, and in this case I get 136 as my answer. Okay, the init value is 100, and the individual elements, resulting elements, contribute to a sum of 36. So in total, my result is 136. Okay. So these are all toy examples just to get the feel of Foreach, but just from this, don't underestimate the power of Foreach. Okay. And I can specify more complex combined functions as well. So in this case, I'm saying for each I equal to 1 to 4. Okay, that means I have input elements 1, 2, 3, and 4 different elements. Okay, and on each of those elements, I am doing R norm of 10. Okay, what is R norm of 10? I am simply generating 10 random numbers. Okay, it has nothing to do with the input. I am just simply generating 10 random numbers, and I am doing that 4 times. For when I equal to 1, when I equal to 2, when I equal to 3, and also when I equal to 4. Okay, so I get 4 sets of 10 random numbers from normal distribution. Okay, and then I'm combining them using cbind. Remember cbind? Cbind is essentially concatenating columns one after the other, right? So what I'm getting here is 4 individual sets of random numbers, and then I'm putting them together column wise. Okay. So what would be the class of RMAT? If I execute class of RMAT, what would I get? Okay, it will not be an array because I'm doing column bind. Okay, individual R norm is an array. So if I simply execute R norm of 10, I get an array of 10 values. Okay, however, if I do cbind of R norm of 10 and then R norm of 10, okay, that means I'm taking 10 random values here and then 10 other random values here and then putting them together column wise. So I get a matrix of 2 columns, right? It's a matrix. And similarly, in this case, since I'm doing it 4 times, okay, because my input elements are 1, 2, 3, 4, I'm doing it 4 times. So I get a matrix with 4 columns, right? So class of RMAT is actually a matrix, and I can do anything that I can do on a matrix. I can say n row of RMAT, which is 10, and then n col of RMAT, which is 4. So it's a 10 by 4 matrix. Okay. Simply whatever you need to understand is I take the result of each of this computation and then I'm combining those 4 results using cbind. Okay. So it's essentially the same thing as cbind of r norm of 10 r norm of 10. So that's exactly what that is. Okay, I'm executing r norm of 10 4 times and then putting them all together using cbind. Okay, let's and we can do a lot of other things as well, right? Let's say you want to compute the mean of every column in your matrix. Okay, so I have a huge matrix with hundreds of columns, and I want to compute the mean of every column, right? And that's a pretty standard operation in typical data processing before you run any machine learning algorithm. You want to compute mean of each column and probably standardize each feature. By standardize, I mean I subtract mean and divide by variance, right? So I can do that using Foreach. And so if you look at this one, okay, actually let's try to write it. Okay, so for each, the goal now is to compute the mean of every column, right? And obviously, how many columns are there? It's given by n col of the matrix, right? So my iteration variable will be I is equal to how many times I need to execute? Essentially, n col of R match. Okay, so those many times. And what would I need to do? In each of those iterations, I want to compute the mean of ith column, right? So mean is a function in R already. And how would I get ith column? R mat of I, comma I. Okay, so this one will get the ith column, and then I compute the mean, and I am executing that for every column in the matrix. Okay, so I simply get 4 different means, and I get it as a list of 4 means because I did not specify any combine function. And if I specify the combine function via dot combine, okay, I get an array of 4 elements, and you can verify that by simply, so there is a function called call means in R, which takes a matrix and produces the mean of individual columns. And not surprisingly, you will get exactly the same result if you do column means as well. Okay. And similarly, I can compute the mean of every row as well, right? If I want to compute that, I'll say for each I is equal to 1 colon n row of R mat. Okay, those many times I need to generate, and then obviously I want to do combine equal to C. Otherwise, I'll get a list of elements. Okay, and then I'll say mean of R mat of ith row. Okay, so this is my 10 means, right? I have 10 rows in the column, in the matrix, so I get 10 different means, and it's the same as row means of R mat, which is again another function in R that we can work on matrices, and I get exactly the same result. Okay. But imagine if you have a huge matrix with million rows and you want to do something on each row, then instead of doing it using a regular for loop, you are able to do that much faster using Foreach and a parallel backend, right? Okay. And these are just more examples. So here I wanted to kind of normalize each of my row. So I want to compute the mean of each row and then divide each element in the row by that mean. Okay, so this is the same as what we have done prior to executing k-means, right? Before executing k-means, we normalized individual features, right? And we wanted to do that so that to account for the magnitude differences in each feature. So imagine I have two columns in the matrix in my input data. One column has values between 0 and 1, and the other column has values between I don't know, 1 million and 2 million. Okay. In that case, k-means whatever I compute. So since 1 million and 2 million is a huge magnitude compared to the simple 1 and 2, in order to account for the difference in those magnitudes, we normalized each row, right? And the way we normalized, we simply take the mean of the row and then divide that mean on by every element, okay? And that's exactly what I'm doing here. Okay, it's actually the same statement. I think copied it 4 times. Okay, so simply I'm doing n row of match so many times, and then and the computation is simply the ith row is equal to the ith row divided by the mean of the ith row. Okay. And then I'm combining all my results through R-bind so that I get a resulting matrix just as the input matrix. Okay? Is that clear to everyone what we just did? We are simply taking the mean of each row and then dividing that mean, dividing individual elements with that row mean. Okay, so we have already seen this particular example. It simply applies square root on each element. Yeah, this one just simply talks about iteration variables and how they change across different iterations. Okay. And also the fact that you can write any computation you want, okay? And these A and B are simply some names. You can put any name here. I can say for Edureka is equal to 1:3 and India is equal to rep of 10,3. Okay, any names. Those are simply iteration variables. Okay. And yeah, this one simply talks about the need. You can write any part of the code in this particular open brace and close brace. It's any random computation that you can specify on these iteration variables. Okay, and each of those iterations are independent of each other. Okay, so there's no cross iteration dependencies that are going in there. Okay, when I'm in the first iteration, I won't try to access elements from a different iteration. Okay, that's not possible. Okay, and this is the combine function, which we have already seen the examples. Okay, and this is exactly what we just did, created a matrix of matrix with 4 columns by using the combine function to be C-bind. Okay, and okay, this is exactly what Sanjay was getting at. How would I execute in parallel? Okay, so as we have seen so far, there's no, I mean, so far we just executed some examples of Foreach, but each of that executed on a single machine in a sequential manner because we did not specify any parallelism in there. Okay, and in order to do something in parallel, instead of doing percentage do percentage, we need to do percentage do par percentage. Okay, so we simply need to replace this part of the expression with do par. That means I'm asking this for each to be executed in parallel manner. Okay, so even with percentage do percentage, for each is already kind of powerful, right? I hope you realize that. It's nice way of expressing the computation instead of writing some complex loops. Okay, so even in a sequential mode, it's already a useful construct, and you can get the real power of the construct by specifying this do par. Okay, and it simply runs individual iterations in parallel. Okay, and how would I run in parallel? I can specify the backend. Okay, I can specify a multi-core backend where multiple threads get spawned and you run them in parallel, or I can even specify a cluster of machines. Okay, let's actually go to here. Okay, so these are the things. So set do par. So first I need to, so this is, as you can see here, the set do par, which is a function in this for each package. This function, set do par function, is used to register a parallel backend with the for each package. Okay, so if you have any parallel backend, a cluster of machines or a multi-core machine, you would set it using this, and then you execute for each with do par, then it gets automatically parallelized for you. Okay, so if you see for each do par, and okay, before we get there, yeah, so you would do parallelism using set do par. Okay, and you can get the complete help on for each using this. We talked about dot combine. There's also dot final, in order, multi combine. There are many other things. Okay, and you can even handle errors. You either want to stop it, remove it, or pass it. Okay, let's say you are executing this enormous computation on million elements. Okay, if one of the elements fail, do you want to just error out and lose all the remaining results, or do you want to simply flag that as an error and then keep going forward? Okay, that's the thing that you can provide via error handling. Okay, so there are many other things that you can do. You can look at the help page for more details. Okay, and this is exactly what the parallel backend is about. Okay, parallel computation depends upon a parallel backend that you register for the computation. Okay, and as you can see here, the parallel backends available will be system specific, but include do parallel, which uses R's built-in parallel packages. Okay, so the bottom line, as we just discussed, is we need to register a backend, a parallel backend, whether it's a multi-core machine or a cluster of machines. And once you register those backends, whenever you do percentage do par percentage, you will run your computation in parallel. Okay, and R already has multiple packages for doing parallel backends, for registering parallel backends. One is do MC. Okay, do MC is the package for registering multi-core backend. Okay, it already has some capabilities to do computations on parallel packages, multi-core machines. Okay, and similarly, there is something called do snow. Okay, it's a network of workstations. That means a cluster of machines. Okay, and using this do snow, you can register a cluster of machines. Okay, so essentially, what you do in order to do parallel processing using Foreach is if you have a multi-core machine, then you install a doMC package, which we just saw before. You install this doMC package, okay, and then once you install the doMC package, you can register a multi-core machine as a parallel backend using set do par that we've seen in the Foreach package, and then you can simply specify %do par %. And then it will run it on a multi-core machine via multiple threads, multiple parallel threads, as Sanjay was talking about. Okay. And similarly, if you want to do a cluster of machines, then I would go with a do snow package. Okay. Snow means, I think now means network of workstations. I don't know. I don't remember what S remember. Probably synchronous. That's how you can get the real power of Foreach to do parallel processing. Okay, another thing that I can do, obviously, so whatever we have seen is some toy examples, but a real world example is to basically build, let's say, parallel random forests, right? I can simply, in each of the iteration, I can execute, I can create a different tree or different random forests. Okay. So in this particular case, so in this particular example, okay, I want to construct 1000 trees. Okay, but I'm dividing that into 250 each. Okay, in each of my part of the computation, I'm constructing 250 trees using our usual random forest call, and then I'm getting all those results and then combining them and then putting them into RF. Okay. Now, if you see RF, I'll get number of trees to be 1000. Okay, this is exactly a more real-world example of doing parallel computation on a machine learning problem. So, essentially, what we have just seen is doing parallel processing using R either on a single core, either on a sequential machine, or on a multi-core machine, or on a cluster of machines. Okay, that's the ability that you can get using Foreach. Okay, and also using the other packages that we just saw, do snow and doMC. Okay, so essentially it's a way to do parallel processing using R. So with this, we are kind of wrapping up on all the concepts that we are going to cover in this particular class. So just to recap and look back, what we have basically done is look at different algorithms from a diverse class of algorithms, class of techniques. Okay, we saw something in a couple of algorithms in clustering, couple of algorithms in classification, couple of algorithms in recommendation systems, and also a little bit about data mining, in particular pattern mining. And previously, I think in the context of k-means, we also talked about like outlier detection. How can we find outliers and how can we remove them and stuff like that, right? So with all this, I hope, and along with this conceptual algorithms from a concepts perspective, along with that, we also looked at how we can use different tools like R and Hadoop, Mahout, and then all these DoMC packages, how we can use these different tools to execute those algorithms. Okay, so we kind of learn some concepts from mathematical perspective, from algorithm perspective, and we also learn how to use these tools in order to execute those algorithms. Okay, so with this, I hope you have enough arsenal in your bag whenever you go to an interview. Okay. And as a couple of you already mentioned in the beginning of the class, you need a lot of practice in order to really appreciate and digest these concepts and understand them in a much more deeper manner. Okay, like the old saying goes, practice makes man perfect. So the more you practice, the more comfortable you will get with these techniques, and you can talk about them in a more confident manner. Okay, so we will stop here for today's class. We'll talk again tomorrow and see you all tomorrow. Okay, goodbye.